So in the previous sessions, we learned the techniques of taking derivatives, right? And earlier than that, we interpreted derivatives as the slope of a tangent line or the instantaneous rate of change of a particular function. So that instantaneous rate of change, come up in a lot of like natural and social sciences. Like for example, in physics, one of the examples that we already saw is the position function. So when you take the derivative of the position function, then it will give you what? The velocity function. And if you take higher derivatives, which is derivative of the velocity functions, we got acceleration function, right? So those are basically talking about the rate of change of the functions. And later on, if you go into physics class, like talking about the electricity, the currents, when you take the derivative of the current equations, that will tells you the rate of change on a float, through the surface. And in chemistry, I sort of pointed out before, in chemistry, when you take the derivative of an equations, that will talk about like, the instantaneous rate of change of the reaction. And, like this COVID-19 things, like if you talk about in biology cases, if you talk about growth functions, then they'll talk about the instantaneous rate of change of the growth. So a lot of things like come up, in the naturals and social sciences. Like another thing is in business will be when you take the derivative of the cost function, that will give you the marginal cost, okay, which is the rate of change of producing one more items. So what we're going to look at is we're going to look at like, the formula that we have talked about before, right? What is the average rate of change? That's basically changing y over change in x. And if you talk about the limit as x, delta x approaches to zero, which is the definitions of the derivatives, and that will interpret it as the instantaneous rate of change. So I will not go into every particular field of like, applications. I'm going to talk about something that I'm more interested in, which is uh, taking derivatives, talking about the applications of physics, and one example is on like, the business part. So the very first thing that I want to do is like, this particular problem. So a particle is moving, according to the law of motions, and I given to you the position functions, which is t over 1 plus t squared, right? That's whenever t is greater than or equal to 0. And time in second, and then position in feet. So the first thing that I'm asking you is to find the velocity function. And then second is what is the velocity at a particular time. And then after that, like, I'll ask you a series of questions, and then next to it, I sort of shows like, what this mean in terms of mathematical, you know, point of view. So we're gonna move on, all of this. So part A is basically asking us to do, right, velocity at time in general. So that's basically talking about the velocity functions, that is taking the first derivatives of the position functions. So when I take derivatives, I will have to use the quotient rule. So the derivative of the numerator, 1 times the denominator, 1 plus t squared, minus the numerator times with derivative of the denominator, 0 plus 2t, and all over, and denominator square, 1 plus t squared, quantity square. And simplifying a little bit, the reason why I want you to simplify is this is the type of problems that we're going to be seeing later on that you need to simplify, because notice that right here in G, I'm asking for the acceleration function, which is I need to take another derivatives out of it. So when I simplify this, right, distributing 1 and then distributing negative t, that will give me 1 minus t squared, and all over 1 plus t squared, quantity square. Okay. So now, to answer part B of this session, this question, which is asking you to find out the velocity at time equal to 3. Right? The velocity at time equal to 3. So substituting that, time into the velocity function that we just found, 1 minus 3 squared all over 1 plus 3 squared quantity squared. So, which will give me negative 2 over 25. Okay, after you simplify it. And this is basically feet per second. Right? And part C basically asks you to find out when is the particle at rest. So asking for what time the particle is not moving. So right here, what we need to understand is this part, when it say particle is at rest, that basically means my velocity is 0. Okay? So, um, so basically what we are asking us to find out is when v of t equal to 0, and what is my t is going to be. Right? So that's the questions, particle at rest. So now what I'm going to do is I'm going to try to find that function value. Right? So v of t, that is basically 1 minus t squared all over 1 plus t squared quantity squared, that is equal to 0. So when I multiply both sides by denominator, that gives me this, and which is I got t equal to plus or minus 1. Right? And we know that the time is not, don't have negative time, so therefore my answer will be particle is at rest when t is equal to 1. Right? 1 is after 1 second. Now, the next questions, part D, is asking us, when is the particle moving forward? So what does that basically means, moving forwards? Like, how do we know moving forwards, right? So this portion right here. So moving forward, that's basically talking about going into a positive directions. And that's happens, right? When the particle is moving forward, when the value of the velocity, right? The value of the velocity function is a positive. Right? So I should say that the function value of the velocity function is positive. Right? Anytime that giving you that, that means like the particle is moving forward. So therefore, moving forward, that means I will need to find out the velocity function is greater than 0. And at what time would that give it to me? So when the velocity function is greater than 0, that's basically say that 1 minus t squared all over 1 plus t squared quantity squared, that is greater than 0. We are solving for rational inequalities right here. And we know the denominator can never be 0, and then we already found out what is going to be 0 of this function. So we know that 0 of this function is t equal to negative 1 or t equal to positive 1. And we already know that this negative is not applicable in this problem. So what do? We basically, like we did in algebra, try to find out the solutions of this inequality, which tell us I'm going to have a real number line, and here's 0, and here's 1. And what are we looking for is the value of v of t, right? The function value of the velocity function. So in the interval 1 and the interval 2, right? And we need to find out what it's going to give us. So now checking it with the number 0.5 right here in interval number 1, I got the velocity functions is a positive value, because when you plug it into right here, 0.5, so this top part will be positive value, then bottom part will be positive value. So therefore, in this interval, I will get positive value. And when I plug it in 2 on an interval number 2, right? And when I plug it in the same thing into velocity function, and the top part will give me a negative value, and the bottom part will be positive, so therefore it will be a negative value. So now we found out that the particle, the function value of this velocity function is positive between 0 and 1. In terms of interpretations, that basically tell me that the particle is moving forwards within this time interval. Okay, so now to conclude this questions, now I can say that therefore, right, particle is moving forward on when the time is between 0 to 1. Okay? So if they ask you, when the particle is moving backward, that's basically talking about what? When the value of the velocity function, right, is negative values. So in this case, anything between, 1 through a positive infinity, the time is moving backward. But that's not what the question asks us. So continuing this, what is the next part of this question, right? So part E is asking you to draw a diagram to illustrate this particle, right? So part E is basically asking you to draw the diagram of it. So if I'm drawing the diagram, and this is basically how is that going to look like in two-dimensional one. So here's my initial point when my t is equal to 0. And then this particle is going to be moving forwards, and then it stopped and then turned around. When it stopped, that means it changed the directions of it. Okay, and then go back. So when is that stop? And we know that the particle at rest when time is equal to 1 from the problem number um, part C, and then it keep on going. So therefore, now I see that my particle is going to be, moving forwards between 0 and 1, and then moving backward 1 to infinity the time. So this is the diagram that we can see. Okay. Any questions so far? All clear, right? So make sure you understand that, what is a moving forward means in terms of derivatives and then mathematical points of view, and then continue from there. So now the next one is asking you to find the total distance traveled during the first 8 seconds. So for this problem, right, total distance on the first 8 seconds. Part F. So when we talk about the total distance on the first 8 seconds, this is usually what we tend to do it wrong. We might be doing s of 8 minus s of 0, and that talk about the first 8 seconds, the distance between 8 seconds and then 0 second, that will give me the total distance. No, that's not true. Okay, so because of the particle is moving forward and moving backward, when you talk about the first 8 seconds like this, s of 8 minus s of 0, that's basically talking about the displacement, not the distance. So you got to be careful with that. Okay, so in order to talk about this first 8 seconds, we already saw the picture already, such that the time is t equal to 0. That's initial, and then it moved backwards and then go like this. So right here is the time equal to 1, and then let's say 8 seconds right here, t equal to 8. So I need to break it down into two situations. First, I need to find out the distance from time 0 to 1. And then I need to find the distance from time 1 to 1 second to 8 seconds. And then adding up those two times together, that will give me the total distance. Follow so far? So from this on, now I can basically look at it as first part, right, is the distance from the time 0 to 1 second, right? So that's the first case. So this is basically S of 0, absolute value of S0 minus S of 1. And when you plug it into the position functions, so I'm not going to write it down detail, okay? You can do that in your calculator. You can give me like this on the test also. You don't really need to tell me like exact. So that will give me, if you plug it into the calculator with the functions, that will give me 1/2. Okay. So remember, we are evaluating in the S functions, the position function. Now, if I continue the same thing, right? Part 2 of this, we need to find out the distance when the t belong to 1 to 8 seconds. And this will basically mean that S of 1 minus S of 8, right? Absolute value of that, because we want to make sure that the distance are positive distance. So this will give me 49 over 130 if you plug it into the formula. So now, finally, I can talk about the total distance, which is the main thing that we want, right? Between, the time between 0 second to 8 second, right? So that's the first 8 seconds. So that's basically, we are adding 1/2 plus 49 over 130. Right? And this will basically give me my final answer, which is 57 over 65 if you use a calculator. And since these are in feet, so make sure you indicate your units. These are feet. All right. Any questions on this part F, finding out the total distance? Okay. If not, then let's move on to the next questions.
Professor?
Yes.
Professor, can you go just up again, just so I could take a picture of the notes on the top? Yeah. Thank you.
So the next question is basically telling you to find the accelerations at the time t, and also the value of the accelerations, right? What is the acceleration after 3 seconds? So that's what the question is asking. So to find out the acceleration functions, I need to take the derivatives of the velocity function. So to do this next problem, g, right? So the acceleration functions, that is basically taking derivative of the velocity functions. So when I take the derivative of this velocity functions, this gave us, right? And remember, the velocity function is right here. Let me pull it up. Right? I'm not going to go all the way up. Like this part right here is a velocity function, right? So when I take derivative of that, that will become derivative of the numerator, which is 0 minus t squared. And then times with denominator, so 1 plus t squared quantity squared, minus, and numerator, 1 minus t squared, times with derivative of denominator, which I need to use the chain rule, which is time 1 plus t squared, and then to the first power, and using the chain rule, which is taking derivative of inside, that will be 0 plus 2t. And all over 1 plus t squared. And when you square it again, this will become t to the 4th power, right? That's what we're going to get. So now what we need to do is we need to simplify this part, right? So that I can continue talking about something else. So when I simplify this, And what you need to be able to see is this part right here, so that you will not be writing down a lot of steps. And on the first term, I have 1 plus t squared. On the second term, I also have 1 plus t squared. So I can factor out 1 plus t squared and reduce with one of the denominator part. That will give me 1 plus t squared. Originally, it's supposed to be fourth power, but because of we reducing it 1, it will become third power. And then continue simplifying on the numerator, right? And this will help us to get oh, I made a mistake right here. Do you guys see that? When I take the derivatives, I only take derivative of 1. I forgot to take derivative of this part. So this should have been 2t right there. Okay. So when I distributed that, this will become negative 2t minus 2t to the third power. Right? Let me do it a different way. Distributing is like, too much work. So what I'm going to do is I'm going to try to write it out so that we can continue a little bit faster. So not distributing, but just write it down. That will be negative 2t, 1 plus t squared minus, and this will become 2 times 2 is 4t over 1 minus t squared. Okay. So now what I'm going to do now is I'm going to factor out negative 2t and then combine it the rest, and this will give me negative 2t. And on the first term, I only left with this. On the second term, that will become positive 2. And then when I distribute positive 2, and then combining it up, that will become 3 minus t squared. All over 1 plus t squared to the third power. Okay. So I skip a lot of step right there on the algebra part. Okay, so making sure that we all okay with this. So now I have my velocity acceleration functions ready. So the question
Professor,
also, yes.
Can you explain that last step really quickly?
This last step,
The minus 2t.
now when I look for the second part of this questions, we want to find out the accelerations at 3 seconds. So basically, I want to substitute into this functions right here, which is negative 2 times 3, and then 3 minus 3 squared, and then 1 plus 3 squared to the third power. So when you evaluate this using your calculator, right, that should give you 9 over 250. And since this is acceleration, this will be feet per second square. Okay. Any questions before I move any further from here? All right. So what is the next question that they're asking for, right? So the next question is asking when the particle is speeding up and when the particle is slowing down. This H and I, we're going to do it together. And why? Because what does it mean by particle is speeding up? Okay, the particle is speeding up when the value of velocity functions and the acceleration function are the same sign, meaning the velocity of a velocity function, right? The value of velocity function and the value of acceleration function, they both have positive or they both have what? Negative. That is what I mean by the particle is speeding up. If the particle is slowing down, that basically means that the value of the function value of velocity and accelerations have the opposite sign. So for the velocity functions, we already know that when it's going to be positive value and when it's going to be negative value in part D. So we need to find out for the acceleration part so that we can compare. Okay? So to find out the acceleration functions, right? For the acceleration function part, so I'm gonna do h and I together. So the first thing that I need to know is I need to know when the acceleration function is equal to 0. So that's basically given to me negative 2t times with 3 minus t squared all over 1 plus t to the second power all the way to the third is equal to 0. So when you clear the denominator, that will be negative 2t times with 3 minus t squared, that is equal to 0. So which give us t is equal to 0, and then 3 minus t squared equal to 0. Okay? So this tells us that my t is equal to 0, and then t is equal to plus or minus square root of 3. So this allows us, right, to do like before. Here's my real number line, and again the time can be 0 or the time can be positive, cannot be negative, so we discard this negative radical 3. And this time what we are interested in is we are interested in looking at the value of the acceleration function. So like before, I'm gonna pick a number, okay, in each interval. But before that, let's try to find out what is the square root of radical 3 so that I can pick the number easily. So the square root of radical 3, that is basically approximately 1.7 something. Okay, so when I pick the number, I'm gonna pick 1 for the first interval, and when I substitute into the acceleration function, okay, when I substitute into acceleration function right here, and the top part will be the first factor is negative, and the second factor is positive, and the denominator is positive. So negative divided by positive, that will be negative value. And then the next part, I'm gonna choose, 3. The reason why is because I already evaluate, a's of 3 already, which I know that is a positive value, so that quickly can be done. Following so far? Now, with this, and then recalling what we did before, okay, on velocity functions. So this is 1.7 approximately. So remember that in the velocity functions, let me do this right here. Recall. The velocity functions, we have 0 and then 1 right here. And our value on the velocity function is a positive right here and then negative the rest. So this is the value of velocity function that we saw before. So now from looking at this two, interval graph, right, then I can start answering my questions for my h. So when is the particle is speeding up? So I can say that particle is speeding up on the time interval of, and notice that from 1 to rod 3, both of them has a negative value, right? Both of them has a negative value. So that's basically tells me from 1 to radical 3 seconds. That's particle is speeding up. And for the I part, the particle is slowing down. When the time is, when the velocity functions and the acceleration function has different signs. So that means from 0 to 1, the signs are different. And from radical 3 to positive infinity, the signs are different. So the particle is slowing down from 0 to 1, union with radical 3 to positive infinity. And that basically conclude this problem. So when you take physics 1, right, you're gonna be seeing this one of the famous, like, the Newton's laws of gravitation. It's basically talking about, this formula F equal to G time little m time uppercase M divided by R squared. That's basically talking about, the force, exerted between two objects with two different mass, or it could be the same mass, right? Is basically, formulated by the ratio with the distance square between them. So as the distance of these two masses closer, and the force of, attraction each other will be stronger. And when the distance between these two masses are, far away, then the force of attraction will be less. Okay? So that basically this ratio formula is talking about. Right? So what we are interested in now is, like, what if I take derivative of this equation respect to something, right? So in this case, the only variable that we have is the distance, because the distance may be vary between two objects, right? Because the mass of the objects, once you start from, those are fixed already. And G is the gravitational constant, so that will be also fixed number. So the only variable that we have is the distance between these two objects. So what if I'm talking about, derivative of the functions, of this force function F respect to the distance? What is that derivative function going to look like? And what does that mean? Right? That's what we are interested in. And then also, like, how do we interpret it? Because we learn how to take derivatives. Now, when we talk about applications, we need to know how to interpret the derivative of the equations or the function. So for part A, if I take derivatives of this F equal to G little m big M divided by R squared, and respect to R on both sides of the equations. Okay? So derivative respect to R on both sides. So for this part, to make it easier for us to take derivatives, I'm going to rewrite it as R to the negative 2 power. Okay? And remember, G, little m, and big M, those are constant. So now when I take derivatives of this will become df over dr. That is equal to G, little m, big M, taking derivative of this R to the negative 2 power, which will give me negative 2 R to the negative 3 power. So that's give us df over dr, that is equal to negative 2 G little m big M divided by R to the third power. So that's the derivatives of it. Now, the question is, how do we interpret this? So what does this mean? Right? So I sort of like explained it to you earlier that, this formula, what this formula is doing, right? So you have two objects with different mass, or it could be the same mass, but the force, right, between these two masses got stronger when the distance between these two masses are, like, close. If the force will be weaker between, attraction between these two masses when the distance between these two masses are, far apart. So when we talk about the derivative of this function, force functions with respect to the distance r, this is what we basically means. So the minus sign basically indicating, right, the force is going to be decreasing, right? So in this case, the minus sign indicate that the magnitude of the force exerted by body of mass m on the body of another, the other mass, the bigger one, right, m, is decreasing. And that's what it means. And also, why is that happening? We all know that the distance between these two bodies are also what? Increasing at the same time, right? So also, distance between two bodies increases. I spelled it wrong. Exerts, right? So that's what basically it's talking about right here. Any questions before I move any further? All right. So the second part of this question is telling you that, suppose that it is known that the Earth's attractions, Earth attracts an objects with the force that decreasing at the rate of 2 Newton kilometer, 2 Newton per kilometer, when the distance is 20,000 kilometer. Now, how fast does the force is changing when the distance is only 10,000 kilometer apart? Okay? So this is a new unit that we haven't talked about it yet, right? I'm just gonna point it out right here. This is called Newton, all right? N. So you can Newton units. You can look at it on Google. If you take physics already, you probably know this notations. Right? Here, so what is this basically talking about, right? So it's telling you that the force decreases as a rate of what? 2 Newton per kilometer on when the distance is what? 20,000 kilometer apart. So that basically tells me that, f prime of 20,000 that is equal to negative 2 Newton per kilometer. That's how it's interpreted, right? Because that's talking about the rate of change on a force. At a particular distance, that's the rate of change, on the force part. So decreasing 2 Newton per kilometer. So now what we are interested in is finding out, what is how fast the force is changing. That means what is the rate of change on the force when the distance is only 10,000 kilometer. So to find this out, so first we need to start from what is a known value that we have, f prime of 20,000, that is equal to negative 2 Newton per kilometer. So what we can do is we can attack on the left-hand side. This is basically talking about, the derivative of the force function with respect to the distance and evaluating at 20,000. So that means we are evaluating this functions right here at 20,000. And remember, G, M, and a big M, those are the constant. So therefore, I will have negative 2 G, little m, big M, all over 20,000 to the third power. That must be equal to negative 2. So from here, if I divide both sides by negative 2 and multiply both sides by 20,000 to the third power, I will get the value of G, little m, and big M, which is equal to 20,000 to the third power. Now that we know this value, I can basically find out what is the f prime of 10,000 kilometer, right? What is the rate of change? What is the force changing? How fast the force is changing on the 10,000 kilometer? So that's basically negative 2, right? Times with, and we know that G, little m, and big M is 20,000 to the third power. So that will be 20,000 to the third power, and divided by my r to the third power right here, which is going to be, in this case, my r is 10,000 to the third power. So if you simplify this, right, that will give me all the 0 will cancel out. 2 to the third power is 8. 8 times -2 is -16 Newton per kilometer. So that's how fast, the force is changing when, two bodies are about 10,000 kilometers apart. So now, is there any questions before I move forward? So for this particular problem, it's telling you that TTC has a factory in Myanmar. Suppose that he estimate the cost in jets of operating X item is given by this function. C of X is equal to 15,000 minus 0.006 X to the second power plus 0.01 X to the third power. So now the first question is asking you, find the derivative of the cost functions evaluating at 120th item producing. What is that value? And then also interpret it, what does that mean? Right? So to do this problem, part A, when we look for the derivatives of the functions, derivative of a constant is 0 minus 0.012. When you take derivatives, you bring down the power and then multiply it out, and then minus 1 to the power, and then plus, and the last part is bring down the power, so 0.03 x to the second power. So simplifying a little bit, that gives us 0.03 x to the second power minus 0.012 x. Now what we want to do is we want to find out the derivative of this function evaluating at 120. So that's basically 0.03, right, to the 0.03 times 120 to the second power minus 0.012 times 120. So when you use the calculator to compute this, that will give me 430.56. Okay? And this is in jet, so KYAT. So that's the currency of the Burma. So finding the derivatives is easy. Evaluating the derivative is also easy. Now, the interpretation part, what does that mean? Okay. So this C prime of X, the derivative of the cost function, that's basically talking about, the instantaneous rate of change on the cost. And very soon, I'm going to help you to define, in business term, this is called the marginal cost, right? We're going to define that very soon later on. So more interestingly, right now, what we are interested in is how to interpret that C primes of 120. So what does that mean, C primes of 120? That is basically talking about the rate of the cost is increasing. I'm saying increasing because the value of C prime is a positive, so I'm talking about increasing. So the cost is increasing at a rate of $430.56 on the productions of 120th item. So we are talking about a particular production case, right? So the C primes of 120 basically interprets the rate at which the cost is increasing as the 120th, okay, item is produced. So that's what it means. Right? So we are talking about instantaneous rate of change at that particular production case. Any questions before I move any further? All right. So now part B is basically asking you to, compare what we found out in part A with, right, the cost of producing 121st item. So if we are producing one more item, what is going to be the cost? Okay. So that basically means, part B, that basically means I need to find out the cost of 121st item minus the cost of 120th item. So from 20th item to producing 121st item, what is the change in the cost, right? So that will tell me how much it's going to be cost more. So this basically tell us putting this 121st into this cost functions using calculator to compute it, right? And making sure that on a calculator, you don't need to punch it in over and over again. You can just recall it, right, from what you already punched it in. Make sure you know how to do that. So that will help you to speed it up. So when I plug it into the functions, right, the cost functions for 121, this is the value that I got, 32, 62, 7.764. Minus when I plug it in 120 into the cost functions, this gives me 32, 19, 3.6. And when I subtract these two, that gives me 434.14 jet. So now that we computed already, right? So this is basically the cost of producing 121st item, which is basically like from 20th item to 21st item, how much do we, cost more? So you can see that it costs what? $434.14 jets more, right? Now, this value, we sort of know that it will be around there from part A, because part A is already telling you that when you are producing 120th item, right, the rate of change on the cost is increasing approximately 430 and 56 jet. So you can see that these two values are very close to each other. Okay. So before I conclude this, I'm going to sort of give you a visualized picture idea so that will lead us, why the next session that we're going to talk about is important. So basically, we're going to do the approximations, right? So if you look at on this picturized idea right here, this is like, let's say this is my cost function, right? C of X. So right here, this is where we are producing 120th item. And right here, we are producing 121st item. So, these two values, right, when we talk about the change in Y, right, cost of 121st minus cost of 120th, the change in these Y value, so the change in this Y value, which is C of 121st minus C of 120, right? That is basically the change in Y value, right? The change in the cost. And how much is being produced, how much is the change, that basically we can already see that is very close to what? The slope of the tangent line, which is the instantaneous rate of change, right, at this part right here, this point right here, C primes of 120. So we know that these two values are very close. So later on, we're going to talk about this derivatives and then, how to approximate for the function value in 2.9, which we're going to talk about approximations. So like I pointed out before, now I'm gonna tell you what actually this means, right? Uh, the marginal cost this term is used in business for this particular situations. Limit as um, delta x approaches to 0 of change in the cost functions divided by change in the numbers of um, items that you are producing, which basically this is the definitions of derivatives, which tell us the C primes of X. Right? So when we talk about the rates of the cost is changing, right? Instantaneous rate of cost changing is basically called the marginal cost in a business term. So to be more precisely talking about it, right? So the marginal cost is the instantaneous rate of change of cost with respect to the number of items produced. Okay, so that's basically what we are talking about. Right here. It's good. So for this sessions 2.9 is linear approximations, because basically from the previous session, the last problem, when I illustrate with the picture, right, you can see that this tangent line can be basically like, close to approximating the actual function value. So 2.9 is basically talk about linear approximations, and it go into further into talking about differentials, which will help us to approximate a little bit easier and then better, smoother. The first thing that I want to talk about is like, changing, fixing my mistake, my typo on the printing. So notice that right here, the linear approximations, I make a typo right here. So make sure you cross it out, and then the equation should be f of a plus f prime of a times with x minus a, which is the equation of the tangent line. Okay. So to start it off with, this is like, what we already know. Let's say I have a functions f of x, right? And we want to find out the tangent line at a point A on the functions, right? So when x is equal to a right here, so therefore my function value will be f of a at this point. So we know that derivative of the functions evaluating at that point, that basically gonna give me the slope of the tangent line. So you can see that, the point a and f of a with the slope of the tangent line, when I put it into point slope formula, that give me y minus f of a is equal to f prime of a times with x minus a. So by adding f of a to both sides, now I got y is equal to f of a plus f prime of a times with x minus a. So that basically tells me the equation of this tangent line already. Okay. So we already know that the function value of the tangent line and the function value of this f functions at a point A, they are both the same. But what we are interested in is like using this tangent line function, right, to approximate the function value on f at a different point. And of course, these approximations will be very, close approximations if the value that we are approximating x is close to a, in the neighborhood of a. Right? So therefore, you can see that the next things that I talk about is linear approximations of the functions at a, that means around a. So this function value can be approximated with the value of the tangent line. Okay? And this equation right here, the equation of the tangent line that we got, we can talk about this as, give us as a name, linearizations of f at a. So we would denote it as L of a. Now we're going to be talking about the tangent line as a function of x. So basically what it's saying is like, as you can see, if I'm talking about my x is right here, and then my value on the tangent line is right there, but the actual value of the function is right here. So you can see that the gap is big right there, right? So the approximation is like, it will be more error. But as you talk about this x is very close to a, right, of this tangent line that we found out. And then you can see that the function value and then the value on the tangent line are very, close together, so that your approximation will be very close. So that's what basically it is talking about right here. Okay. So now, before I continue, right, is there any questions on this introductory part? So example 1 is basically asking us to find the linearizations function, and then of the functions f equal to cube root of x at a particular point when x is equal to 8. So first question is finding out the linearization function first for this particular function, f. And then after that, we use the linear approximations to approximate the value, cube root of 8.05 and cube root of 25. So to find out the linearization functions, right? And what is a key thing that we need? We need to know the derivatives of the functions evaluating at that particular point, because that's basically referring to the slope of the tangent line at that particular point. Because remember, linearization function is basically a fancy name for equation of the tangent line. So now, first, my functions f of x, that is equal to x to the 1/3 power. So therefore, when I take derivatives respect to x of these functions, which will become 1/3 x to the negative 2/3 power, which give us, simplifying a little bit, that will be 1 over 3 times cube root of x squared. So to find this linearization functions, first I need the point for, so what is the function value at 8? That is basically cube root of 8, which is equal to 2. And what is the slope of the tangent line at 8, right? Which is going to be f prime of 8. That will be equal to 1 over 3 times cube root of 8 squared. So which is going to be 4 times 3 is 1 over 12. Now, put it into linearization function, which is L of x, that is equal to f of 8 plus f prime of 8 times with x minus 8. So this gives me f of 8 that is equal to 2 plus 1 over 12 times x minus 8. So simplifying a little bit further, that will give me 1 over 12x. Multiplying 112 times 8 is 2/3, and then 2/3 minus 2/3 plus 2, that will give me plus 4/3. So this is the linearization functions for this particular functions at that point. So the approximation will work well when x is close to 8. And we're going to find that out very soon. So why? Because this is the first part of the question that's asking. And the second part of the question is asking you to approximate, right, to do the linear approximation for cube root of 8.05. So that's basically talking about looking for the function value of 8.05, which is, when we do the linearization, linear approximation, this is basically approximately equal to linearization functions evaluating at 8.05. So this gives us 1 over 12 times with 8 plus 4 over 3, and which will give us approximate answer when you use a calculator. Right? And this will give us 2.00416667 ... right? Let's continue on. So we got approximations already right here, right? That's the linear approximations. Now what I want you to do is compute the actual value. What is the actual value? Which is cube root of 8.05. What do you get when you compute it? Okay. I missed the calculator. So, oh, I don't even have a cube root. Scientific. Okay. So 8.05 to the power of 1/3. Oh no, this is not right. But anyway, do you got your answer already? It should be close. Okay. So if you continue on the next one, function value evaluating at 25, which is cube root of 25. If I use the linearizations functions evaluating at 25, and this will be 1 over 12 times 25 plus 4 over 3. And this will give us approximate answer 3.14666667. But if you actually use the calculator and then compute cube root of 25, and you will be seeing that this answer, approximation answer, and the actual answers have a big difference, right? A big difference right there. And that's predictable, right, from the introduction that I'm talking about earlier, because this linear approximations works well on around x equal to 8, but 25 is very far away from 8, so therefore the approximation will be off. So any questions? So I made a mistake right here. Instead of 8.05, I put 8 earlier, so make sure you change that. Okay. And now continue to the next example. And the next example is, you're gonna have to look at it a little bit like, twist around right here. So almost everything the same except like, something else. So the second example is asking you to find the linear approximations of the functions f of t that is equal to cosine of 2t at t equal to 1/2. And we want you to use the linear approximation to approximate the value of cosine of t, 2. So first, I need to find out what is the linearization function is going to be to do the linear approximations. So knowing that f of t that is equal to cosine of 2t, taking derivatives respect to t, that will give me negative sine of 2t. And using the chain rule, taking derivative inside, that will give me 2. So therefore, I got negative 2 sine of 2t. To find out the linearization functions, I need to know the function value at half. So that is cosine of 2 times 1/2, which will give me cosine of 1. And then I need to know the slope of the tangent line at that point on the curve. So that is evaluating the derivative functions at half. So that will give me negative 2 times sine of 2 times half, which will give me negative 2 sine of 1. So now that I have information about the points on the curve and then also the slope of the tangent line at that particular point, now I can write down my linearization functions, which is L of x, that will be equal to f of 1/2 plus f prime of 1/2 times with x minus 1/2. Are we all okay with this? And which give us, this will be cosine of 1 minus 2 times sine of 1 times with x minus 1/2. So that is our linearization function. So now what we want to do is we want to use this linearization function to do the linear approximations for the value of cosine of 2. So here's the questions. What is the value of cosine of 2? And here's the important part that you need to, know, because I need to know exactly where my x is going to be. So you know what? I'm going to use this. I'm going to change this because every input right here is t. So I'm going to change with t right here on my linearization functions. Okay. Otherwise, it will not be consistent anymore. So make sure you change that. So t right here, t, and then t minus 1. So now cosine of 2, that is basically, we are talking about cosine of 2 times 1. And the reason why I write it like this is to help you to see that in the original function, f of t is equal to cosine of 2 times t. So how do I get cosine of 2? My t must be equal to 1. So that basically indicating cosine of 2, that is basically talking about we are evaluating f functions at 1. Okay. We are evaluating f functions at 1. So only if I know which input value that we are evaluating, then we can talk about the linear approximations. So now I can say that f of 1, that can be approximate with the linearization functions at 1. So this is the linear approximations. So therefore, now I can basically compute this by cosine of 1 minus 2 times sine of 1 times with 1 minus half. So which will give me approximately cosine of 1 minus, so 1 minus half is half, half times 2 is 1, so it'll be minus sine of 1. And you may leave your answer like this, or if you use a calculator and approximate it, this will become negative 0.30116879, and so on and so forth, right? And that's basically help us to get the value. Now, what you want to do is you want to, use your calculator and then compute cosine of 2. See that this linearization's approximation is close enough or not, right? And remember that this linearization function is formulated around t equal to half, and then we are evaluating at t equal to 1, so it's about like 0.5 away. Okay? It's not that far, it's not that close, so there will be some error that we're gonna have. And another thing that I want to point out is when you are computing this trigonometric function, make sure you are in a radian mode, right? Because these are not degree, otherwise you're gonna mess up. So is there any questions before I move into the next topic? So first off, what we want to do is we want to look at, like, what is the differential means, the definition of it, and how are we going to use it. So up to now, right, these expressions that we have talked about so far, dy over dx, which is the derivatives of a function with respect to x, look at it as a single symbolic, right, part. And we don't, in this sections, we want to know what is this dy and then dx alone means. That's what we are interested in, okay? So we need to know how to interpret dy over dx as a ratio of dy and dx, which is two separate values, right? So that's what we are interested in on this definitions. So as usual, right, we can say that let x be a fixed number. So I can say that here's my x, and for this function's f of x. So therefore, this has become my f of x value. So what happened is this dy, right, and dx, they are called the differentials. Okay. So the differential of x, it will become the independent variable, which can be assigned the arbitrary value, and the differential of y is become a dependent variable, which depends on the value of x and then dx. So what we are talking about is basically, if I'm having another point right here, right, and this will become the change in x become my dx. So this is x plus delta x. So dx and then delta x will be the same. And the change in y in this linearization functions, right, that will be considered as dy. So now what's happened is the slope of the tangent line, right, the slope of the tangent line can be interpreted as, dy over dx. So dy is a value and dx is a value. So when we talk about the differentials, right, if y is a function of x, where f is differentiable at x, meaning this function is differentiable at a particular x, then the formula for the differentials of y is given by f prime of x times dx. Okay. And when the value of dx is not equal to 0, if we divide both sides by dx, then we will get back into the differential derivatives format. Dy over dx is equal to f prime x. So now we can basically talk about dy over dx as a ratio, okay, and which interpreted as the rise over run of the slope of the tangent line. Is there any questions so far before we move on from here? So another thing that we want to make clear is, the increment dy, which is the change in the y value of the functions. How is that different from the differentials? Right. So as before, let's say that this function is f of x. And so therefore right here, the a point x, I have a function value f of x. And since the function is differentiable at x, then we will be able to find out the slope of the tangent line at that point, and then therefore we can find out the equation of the tangent line at this point, which is, oh, I'm using A, so I'm gonna go along with A, okay? So that way everything will be in the same thing. So at A, so we will be able to find out the slope of the tangent line at A. So therefore we will have an equation of the tangent line at A. So the equation of the tangent line is basically y equal to f of A plus f prime of A times with x minus A, right? That's the equation of the tangent line right here. And now what we want to find out is this, right? And this is the part that I mentioned it, like, earlier, how, how the approximation is working. So now I want to find out the function value at A plus delta x on the tangent line. So let's call this point right here, right? And this is my A plus delta x. So if I found out the value at A plus delta x, that basically means I'm going to be substituting this A plus delta x into this functions, right? The tangent line functions, tangent line equation. So that means y by input will be A plus delta x. That is equal to f of A plus f prime of A. And my x right here would change it into A plus delta x minus A. So when I simplify it, A and A cancels out, so it will left with delta x alone. Okay? So now the y value, right? The function value at A plus delta x on the tangent line is equal to f of A plus f prime of A times delta x. So from before, we know that, right, the change in x for this tangent line, we have differential over x, which is equal to the delta x. The change in y values on the tangent line, which is A to, this A plus delta A, that is talking about the differential of y. And this is basically can be looking at as, right, the change in y value, which is basically going to be looking at as y A plus delta x minus y of A. But we know that this y of A, right, the function value on the tangent line is the same thing as the function value on the curve of the function f. So this portion, that is also equal to f of A. So that's why we are seeing right here my y's, the change in the function value on tangent line from A to delta A, that is basically y of A plus delta x minus f of A, which is equal to what? My right hand side, f prime of A times with delta A. So let me stop right here, and then do we have any questions so far? So now what we want to look at is how do we look at the approximation of the functions. So as you can see that this, the change in the function value on the tangent line from A to delta A is basically this part, right? And which is from here to there. Now, the change in the function value of f, now I'm talking about this part. Let me use the different color. From here all the way down to here, that is denoted as delta y. And this delta y is basically f of A plus delta x minus f of A, right? So you can see that there is a gap, right? There is a gap between this dy, right? Differential of y and delta y. Here's the gap that we are talking about right here. And if you can minimize that, then our approximation will be better, right? So therefore, now what I can talk about is the change in the function value of on the curve of f from A to A plus delta x. that is basically f of a plus delta x minus f of a, that which is what? Delta y. And now I can see that this delta y can be approximate with the differential of y, which is basically using this formula right here. The derivative of the f functions evaluating at a times with the delta x. So that's the connection, and then the distinguish between the difference between the differential of y and the delta y. What is the differences? Okay. So is there any questions before I move forward and then doing the examples? Now let's move to the examples of it. So first we want to know how to find out the differentials of the function. So for this first example, w is equal to x to the second power times sine of 2x. So what we can do is we can look at this as, right, w as a functions of x. So therefore, the differentials of this w, that will be equal to the functions evaluating at x times with dx. Okay. So now what's going to happen is when we, follow that, this will become dw, that is equal to taking derivative of this product, which is going to be 2x times with sine of 2x plus now taking derivative of the second factor, which I need to use the quotient chain rule. Derivative of sine is cosine of 2x times with derivative of inside, which is derivative of 2x, is 2. And then times with dx. Simplifying a little bit, that will become dw, differential of w, is equal to 2x sine 2x plus 2x squared cosine 2x, and then times with dx. So this is basically the differential of the function. For the second problem, we're going to be looking at y is equal to square root of z plus 1 over z. So I'm going to look at y as a function of z. So my differentials dy, right, will be equal to f prime of z times with dz. So now, taking derivatives, so differential of y, that will be equal to derivative of the f function, which is this part right here. So that will be using the chain rule, bring down 1/2 times with z plus 1 over z of negative 1/2. Now, because of the chain rule, now I have to take the derivative inside, which is going to become, using the quotient rule, derivative of the numerator is 1 plus 0 times z minus z plus 1 times with derivative of the denominator, which will give me 1, and all over z squared. And then don't forget, we need to multiply everything by dz. Simplifying this, that will give me dy, differential of y, is equal to 1/2 times with changing this into positive exponent by reciprocating the base, which is z over z plus 1 to the 1/2 power, and times with simplifying the top part right here, z minus z plus 1, so which will be 1 over z squared times with dz. So this is my differential of the function. Any questions before I move any further on this, finding out the differentials? So moving to the next example, right? Example 4. So that will help us to see, like, the difference in values. So first, it is asking us to compute differential of y and delta y's on this particular curve, and from x equal to 2 to x equal to 0.3. So first thing, when we look at this, we know that the change in y, right? Let's find that out because that's easy. That's basically talking about the change in y value, which is y evaluating at 2.03 minus y evaluating at 2, right? The change in y value of the functions. That's what this delta y means. So when I use my calculator and then approximate it, so make sure you put it into radian modes, because this is the sine and cosine will be in radian function. So this gives me 0.0835812 dot dot dot. Right? I got this. Now, what we want to do is we want to look at what is the differentials. So to talk about the differentials of these functions, right? And I need to look at my y as a functions of x. So therefore, my differentials of y, that will be f prime of x times with dx. So from here, what we need to find out is what is my dx is going to be. So remember that dx, that is basically talking about the delta x, right? Which is, in this case, is 2.03 minus 2. That gives us the value of 0.03. And now we want to find out the differential functions, right? So that I can basically continue. So where are we centering at? We are centering at 2. That's what we need to remember. So therefore, my differentials dy, that is equal to derivative of the functions, which is derivative of cosine, is negative sine of everything inside is the same, times with, using the chain rule, taking derivative of inside, which is 2x plus 0, and then times with, not times with, minus derivative of x, that will be 1, and finally multiply with dx. So now differential of y, simplifying a little bit, that will give me negative 2x sine of x squared plus 1 minus 1 and times with dx. And what are we evaluating? We are basically what? Evaluating at, that at 2, right? The differential at 2 with the delta x, dx become 0.03. So that's why in the beginning I mentioned it before, this differential of y is dependent variable respect to x, okay, where your initial point is, and your delta x. So when we are evaluating this, this is basically dy is evaluating at x equal to 2, and the delta dx is equal to 0.03. So which give us, when I put it into the formula, right? So that will become negative 2 times with 2, and then sine of 2 squared plus 1 minus 1, and then times with 0.03. And when I compute this, this will give me approximately 0.0850709 1 dot dot dot. So you can see that the change in y value of the original functions and approximations up to, 2 or 3 decimal points accuracy right here, close to 2 decimal point accuracy for this one. So that's basically like, later on what we are interested in is using this idea together with what you learn in the, chemistry or physics lab, finding out the, relative error to see that your error is a significance or not, to talk about, conclusions on your project or your researches and so on and so forth. So is there any other questions before I move on? So moving on to the last example, and this is where you will really see that, why this differential idea is a lot, useful. So now example 5 is talking about use the differential to estimate the amount of paint needed to apply 1 coat of, not point, make sure you change that, 1 coat of paint, right? That is 0.05 centimeter thick to a hemisphere dome that had with the diameter of 50 centimeter. So we are trying to estimate what is the volume of the paint that we need before we even start computing. So here's a picture of what we are looking at. Here's a atmosphere. And with this atmosphere, we know that this diameter is 50. So we know that the radius is 25. And we are trying to apply a coat of paint on top of this atmosphere. So that basically talking about the thickness of this paint right here, right? It must be, the given part right here, the thickness must be 0.05 centimeter. So to apply that, paint, and what is the volume that we need? So far, what we know is, we know the diameter, that is 25 centimeter. And this little, extra part, that is basically talking about the R, okay? So the differential of R, which is going to be 0.05 centimeter. So now the question is, do we remember, okay, the volume of a sphere? So here's the recall. The volume of a sphere is 4/3 pi r to the third power. So now with this, since we are talking about hemisphere, our volume is only half of this. So we are talking about the volume is equal to 2/3 pi r squared. So to estimate, right, the volume of this thickness that we need, right, we want to use the differentials. So we can talk about the differentials of volume V, that is equal to 2/3 pi times the derivative of r squared, which is going to be 2r times dr.
Isn't it r cubed?
Oh, r cubed. Thank you. So I made a mistake right here. So r cubed. So this will become cube and then 3 and a square. Thank you. Copied it wrong. So now, if I simplify a little bit, that will become the differential of V, that is equal to 2 pi, right, r squared times with dr. So notice that this formula, this differential formula, will help us to, estimate for any thickness that we want for this particular diameter or any other diameter that we were going to talk about later on, right? So those are the variable that we have. So that's why I mentioned it before, this differentials of, V, in this case, the volume is depending on the diameter of this hemisphere with the dr, which is the thickness of the paint that you want to put it on. So now I can approximate the differential of V with respect to R equal to 25 and then dr equal to 0.05. So which will help me to do the computation of 2 pi times with 25 square times with 0.05. So approximately, this will give us, if we use a calculator, right? And that will give me approximately 196.35 centimeter cube. So now we found out that, right, the volume that needs to be by, right, to have one coat of the paint with the thickness of 0.05. So now the interpretation, final interpretation will be approximately needed 197 centimeter cube of paint. And that concludes my problem in this case. Now, this approximation, is that right or not? We can easily find that out, right? By looking at the actual value. So what is the actual value? We want to find out the volume of that little blue line that I draw, right? That means we want to find out the volume of the hemisphere with the radius of 25.05. That's the whole thing, minus the volume of 25, which is before you paint it. And the difference in this y value, that should be close to this differential that we found out approximations, okay? Because that's very, very close, because we only want 0.05 thickness. So what is the approximations of this value right here, right? So plug it in this into the volume functions right here, and then computing it and then subtracting it, that will give me approximately 196.74 centimeter cube. So you can see that the approximation values are, very close right here. And any questions on the sessions in general?